Welcome to today's Explainer. We're jumping straight into a true mathematical detective story. Seriously, this is the tale of Gerd Faltings, a brilliant German mathematician who didn't just solve a ridiculously difficult equation. He fundamentally reshaped how humanity sees numbers, geometric shapes, and really, the very edges of infinity itself. We're going to look at exactly how he pulled off the impossible and transformed our understanding of the whole mathematical universe.
But first, to really wrap our heads around the sheer magnitude of what Faltings achieved, I want you to picture something for me. Imagine you are standing in the middle of a massive, sweeping, endless desert. Now, how do you count exactly 1,000 specific grains of sand out there? Take a second to really visualize that. It sounds literally impossible, doesn't it? Without a clear boundary, you can't. And that exact feeling of impossibility, that perfectly sets up the central mathematical mystery we're unpacking today.
Because the mystery we're talking about wasn't just some tricky homework assignment. No, this was a 60-year-old mathematical cold case. We are talking about a puzzle that, for decades, had absolutely baffled the world's smartest minds. Generations of geniuses had tried to solve it, and for decades, every single one of them hit a massive brick wall. You can imagine the frustration in the math community. It was palpable. It built up this incredible narrative tension around a problem that honestly just seemed unsolvable. To understand why it was so hard, we have to look back. For centuries, familiar math equations acted kind of like predictable treasure maps. Think of the Pythagorean theorem from school, right? A squared plus b squared equals c squared. If you map that out, it actually creates a landscape with an endless, infinite supply of nice, neat, whole number answers like 3, 4, and 5 stretching on forever. For mathematicians, it was this comfortable, endless sea of solutions. But then things get messy. When mathematicians started playing with more complex equations, the kinds with higher powers and wild, curvy shapes, that endless sea of answers, it suddenly just vanished. The complexity introduced this sudden scarcity, and the numbers literally dried up. Mathematicians were left scratching their heads wondering, wait, are the answers gone completely, or are they just hiding somewhere in dimensions we can't see? That brings us to 1922, when a British mathematician named Louis Mordell made a totally radical prediction. He was looking at highly complex equations that, if you were to actually draw them out, look like shapes with multiple donut holes in them. And he made a bold claim. He said that once a shape has enough of those holes, the endless sea of neat, whole number answers just stops. It completely dries up into a strictly limited, finite number of solutions. Now here's the core frustration of that era. Mordell made this massive claim about a finite limit, but he had absolutely zero way to prove it. Asserting a specific, limited number of solutions without a mechanism to calculate them is exactly like our desert analogy. It's like claiming that huge, endless desert contains exactly 1,000 grains of sand, but you don't actually have any way to count them. It was a brilliant hunch, sure, but it remained entirely unproven for 60 long years. Enter our protagonist. Fast forward to the early 1980s. While most 20-somethings were, just figuring out their early careers, a 29-year-old German maverick named Gerd Faltings decided he was going to crack this impossible cold case. He looked at a problem that had literally defeated generations of older, deeply established geniuses, and he just decided to dive right in. So how did he do it? Well, Faltings realized pretty quickly that the old brute force method, just crunching numbers harder and faster on a chalkboard, was a total dead end. Instead, he completely shifted his perspective. He stopped looking at the raw numbers themselves and started looking at the spatial structure, the beautiful, twisting geometric shapes that those numbers actually created. To pull this off, he needed an entirely new set of tools. His solution actually required elements from 3 completely distinct mathematical worlds that almost never spoke to each other. He needed number theory, which is the study of numbers, geometry, the study of rigid shapes, and topology, which is basically the study of how shapes stretch and bend, almost like they're made of rubber bands. Then came the magic. In his 1983 breakthrough, Faltings essentially engineered rigorous theoretical bridges between these totally distinct worlds, and he proved something truly mind-bending. He showed that the way a shape stretches and bends like a rubber band actually controls the rigid, unbending numbers trapped inside of it. He basically proved that these isolated mathematical worlds were secretly speaking the exact same language all along. And by connecting those worlds, Faltings finally cracked the cold case. He proved, once and for all, that Mordell was right on the money. For those complex, multi-holed donut equations, the sea of infinity truly does dry up. Faltings found the definitive, hard boundary of the infinite, forever changing how mathematicians categorize the limits of equations. As you can imagine, this stunning breakthrough launched him straight into the stratosphere of mathematical legends. It led to what some people actually call the Grand Slam of mathematics. At just 32, he won the Fields Medal, which is often called the Nobel of Math, but it's strictly awarded to prodigies under 40, once every 4 years. Then, decades later, he was awarded the Abel Prize, which is the true equivalent of a Lifetime Achievement Award. No age limit, awarded annually, given for sustained, profound impact.
And the details of his Abel Prize are amazing. Announced for 2026, Faltings is actually the first ever German mathematician to receive it. Awarded to him at age 71, the formal ceremony takes place on May 26th over in Oslo. It's literally presented by King Harald V of Norway, and it comes with a massive reward of roughly $700,000. Honestly, it's the ultimate capstone to an absolutely brilliant career.
But we have to remember, the Abel Prize honor sustained relevance. His 1983 discovery of those theoretical bridges, it isn't just some piece of history locked away in a dusty textbook. Not at all. His work from over 40 years ago still acts as the absolute foundational bedrock, the master blueprint, for mathematicians who are exploring the universe of numbers today.
So, what is the ultimate lesson we should take away from Faltings' story? I think it's this. When you are faced with the most intractable, seemingly impossible problems, you rarely need a more complicated tool. What Faltings showed us is that we really just need the intellectual bravery to abandon our usual, comfortable calculations and observe the problem from an entirely new viewpoint. Changing the angle literally changes everything.
So I want to leave you with this final thought. Think about the challenges you're currently facing. What impossible problems in your own life, your work, or your studies could you solve right now by simply changing your point of view? Sometimes stepping into a completely different neighborhood of thought is all it takes to find the ceiling on your own infinite desert. Keep questioning, keep shifting your perspective, and thank you so much for joining me on this explainer.